In this post, we'll get to grips with neural networks. This involves stacking the neurons that we've studied in the past two posts into layers. The outputs or activations of neurons in one layer serve as the inputs into the next layer. This happens until we reach an output layer. As we'll see, this means that our neural network is just a function that maps a set of inputs into a set of outputs. While it's just a function, it's fair to say that it is a large and complicated function. This function has a very large amount of parameters. These parameters can be tweaked to map inputs into outputs. This tweaking of parameters happens while a network is learning or being trained. Training a neural network will be the subject of the next two posts. For the remainder of this post, we're going to look at the architecture of neural networks. We'll show how this architecture differs from conventional IT techniques. We've seen in the previous posts that artificial neurons are pretty simple. Each neuron has an output or activation. That activation is derived from inputs. We use some straightforward arithmetic. We multiply inputs by weights and add these products up. We add a bias term. Finally, we pass this total through an activation function. We've said that for the activation function to be useful, it needs to be nonlinear. We've also said that we'd like an activation function's derivatives to be simple to compute. We've justified that statement about the importance of simple derivatives in a vague way. We've said that it has something to do with how a network is trained. We've promised that we'll discuss this training in a future blog post, and we will. But first, we need to discuss how these neurons are connected together to form networks. And that's the purpose of this post. We've covered the neural bit of neural networks. In this post, we're going to address the network bit. When imagining computer systems for automating our business, we think in standard terms. We think about the inputs into our systems. For an equities trading system, we look at things like the ticker, the price, the quantity, buy, sell, and other deal parameters. For an interest rate swap back office system, we'd have many inputs, including counterparty, currency, notional, maturity, fixed and floating rates, payment frequency, etc. It's then common to consult with subject matter experts. These people help analyse process flow and functionality in a system. This would be represented as a set of requirements from which designs can be drawn up. The rules that govern how this business logic is executed can be understood. Experts would also understand how to deal with exceptions. All of this would then be coded up using logic. We've seen huge productivity gains in the past half a century based on the ability to automate businesses using this approach. AI systems work in a completely different way. Rather than starting out with a set of inputs and business rules and then applying these business rules to generate outputs, AI starts out in a wholly different way. It starts out with a set of known inputs that match known outputs. AI then figures out the patterns that match the inputs to the outputs. The AI mapping inputs and outputs approach is thus very different from traditional methods of applying computer systems to solve business problems. Frankly, the types of problems that AI is best suited to are different. Generally, AI is not a great solution for processing systems, but it is great at things like pattern matching, regression, classification, and estimation. Now, the reason for this discussion, comparing conventional systems to neural networks, is to develop an intuition for what neural networks are, an understanding of the problems that they're suited to, and an understanding of how they differ from conventional IT approaches underpins this intuition. Conventional systems can be described with familiar notation: flowcharts, state transition diagrams, database schema, all that stuff. These artifacts are not so useful or common when describing AI systems, neural networks in particular. In contrast to conventional systems where functionality is contained in blocks, neural networks are made up of loosely connected layers of individual neurons. An input layer takes in data from sensors or observations. This might be a market data feed, company fundamentals from an annual report, or pixel intensities from a camera. An output layer gives the results of the network. This output layer might contain a single neuron. For instance, an options pricing system might output the fair price of an option, or the output layer might contain two neurons for a market-making system outputting the optimal bid and offer quotes. In computer vision systems, it's common for a network to have dozens or even hundreds of neurons in its output layer. In these classification systems, each output neuron will identify the likelihood of a particular object that it has been trained to see. Between the input and output layers are hidden layers. Neurons in these layers receive activations from neurons in preceding layers, and they send their output activations to neurons in the next layer. So, one literal and useful way of looking at neural networks is as a huge, frankly vast, multi-parameter, multivariable function. We've seen how each neuron has inputs, weights, biases, activation functions, and outputs. When connected in layers and with several neurons per layer, the number of parameters can become very large, very fast. In high school, we're used to seeing equations in this form: f of x equals ax squared plus bx plus c. Here we have a single input, x, a single output, f of x, and three parameters, a, b, and c. We can draw the graph of this function that maps the input x to a single output y. Even for the most basic neural networks, there are way more than three parameters. Now, a lot of parameters can be a lot to get your head around, but it's these tweakable parameters that give neural networks their power to adapt and learn. For the relatively small network shown on the screen, we have 4 outputs and 10 inputs. There are 3 hidden layers, which contain 8, 6, and 5 neurons. In total, this network has 201 weights and biases. This means that there are 201 tweakable parameters. These parameters allow the network to learn the mapping between these 10 inputs and 4 outputs. Let's look at a practical example from financial markets. Neural networks have been deployed to address some of the shortcomings in closed-form option pricing models. There's no doubt that closed-form parametric solutions for options pricing, such as Black-Scholes, have had huge success. They're simple to understand, intuitive, and the analytic formulae means they're easy to code and compute. But these models contain assumptions. The outputs depend intimately on the form of an underlying asset's price dynamics. An asset's volatility is often modeled as a single fixed parameter in these types of equations. Using a neural network permits pricing via a non-parametric approach. An asset's price history can be fed into the model as a time series, along with strike price, time to maturity, etc. We define the output to be the observable market price of the option. Through training, the network learns to map the inputs into the observed derivative price. Thus, the neural network learns the mapping between the observable inputs to the model and the market price of derivatives. It becomes the model, but it's not subject to some of the assumptions in the analytic models, namely the assumptions of prices being log normally distributed or fixed interest rates over the term of the option. They're also adaptive to structural market changes, such as liquidity, in a way that classical closed-form solutions are not. So in summary, neural networks are made up of layers, with neurons in one layer feeding their activations downstream to neurons in the next layer. There are 3 types of layers: input layers, hidden layers, and output layers. Neural networks differ from conventional IT techniques. There are no formal business rules or processes that operate on input data to generate a workflow. Instead, both inputs and outputs are presented simultaneously to the network. The network tweaks its internal parameters so that it can correctly map inputs to outputs. This means that neural networks are not well suited to many data processing tasks, but they have shown great promise in regression, clustering, classification, and non-parametric modelling. In the next couple of blog posts, we'll start to explore what makes these types of AI solution useful: their ability to learn.